Now, for my capstone project, I did receive permission to join the HMS Paleo team and chronicle the discovery of their Dimetrodon fossil, whom they named Willi, and the efforts it takes to get that from the ground to the museum. And I'm going to do that by highlighting two themes. Come on in. The first theme we're going to do is the narrative of Willi's story, his discovery, his excavation, his cleaning and mounting. But equally important, I want to talk about the science behind the story. We're going to define the animal. We're going to talk about Permian geology and ecology. And we're going to talk about how we find fossils and how we date them. First, a little history of paleo in north central Texas. Our story begins in 2006 when David Temple of the Houston Museum of Natural Science contacted Craddock Ranch owner Bill Whitley about looking for fossils on his ranch. The ranch is located here in Seymour, Texas, in Baylor County. More importantly, though, the ranch is located in the middle of the Texas Permian red beds. This is a preeminent site for looking for early Permian fossils, and it's a site that scientists have been exploring for over 100 years. Some of the early historical figures that relate to the Texas Permian include Edward Drinker Cope. Cope was a famous paleontologist from Philadelphia. Many people recognize his name because he's one of the guys that conducted the Bone Wars. He and Othniel Marsh were two preeminent paleontologists of the turn of the century who were trying to see who could be the #1 guy in the United States. And they would hire fossil hunters to go out and scour the United States and look for fossils and send them just back to them so that they could be the ones who named the fossil. They could be the ones to write up the scientific papers. Now, Cope hired people to go to Texas. And with that, he was able to name over 30 new Permian species. One of the guys that he hired was Charles Sternberg, a renowned fossil hunter from Kansas. Now, Sternberg kept journals of all of his work, and he's the first one to mention the Craddock Ranch as a fossil site by name. Because of his work, the Craddock Ranch has fossils in museums around the world, including a large Dimetrodon that he discovered in 1917, specifically at the Craddock Bone Bed, where we picked up work as well. And finally, I want to mention Samuel Williston. He was a preeminent scholar of Permian vertebrates. He was a professor at the University of Chicago, and it was his team when he was leading a group of graduate students on a field study trip in the Craddock in 1909, where they discovered specifically the Craddock Bone Bed. Now, the Craddock Ranch today is owned by Bill Whitley, the great-grandson of ranch founder E.L. Craddock. And Mr. Whitley continues to support the family's belief that the fossils should be shared with the public. He's very proud that fossils from his ranch are in museums around the world, but he's even really more excited that coming up next year, that fossils from his ranch are going to be on display in Texas for the first time. So, this is the geological map of Texas, and this blue part right here is the Permian era, but we're really interested in this little strip of blue-gray right here. This is called the Clear Fork Formation. It's a strata of rock that can then be subdivided into 3 parts: the arroyo, the choza, and the vale. Now, this land was a coastal plain, and it was laid down by deposition. That means that rivers bring down sediment, and the coastline would expand. It laid down from east to west, so the arroyo, the land on the east side, is going to be the oldest. The vale would be the middle, and then the choza. The Craddock is located in the arroyo formation. Oh, wrong way. There we go. So now let's talk a little bit about the Paleo team and finding Willi. Our HMS Paleo team is led by curator Dr. Robert Bacher and associate curator David Temple. Now, these guys were excited about exploring the Craddock because of its historical reputation for exceptional fossils. But there was an addition, that in addition to finding a stellar specimen for our new Paleo Hall, they also wanted to expand our knowledge of the Permian environment. The past explorers, the guys that we just talked about, they were vertebrate anatomists, and they were only interested in obtaining the most perfect skeleton. So they would just grab and go and never look at anything else around them. Our team would take the time to map the location of every bone that we found. We would analyze the soil samples where the bones were found. And our hope in this then is to use the discoveries to paint a clearer picture of the Permian, the way these animals interacted with each other and what their environment was like. The first step is we explored the ranch for potential sites. And you'll see everybody walking with their head down. That's really true. Every time I've been out to the ranch, everybody walks around like this because you never know if you're going to see something. Nobody, we're talking to each other, nobody looks. Just, we need to leave the door open. So don't close it all the way. Anyway, so exploring the sites, and they decided they would stick with the Craddock Bone Bed, in a site not very far from where Charles Sternberg had found his initial Dimetrodon. Now we've looked at other locations and we've explored some other sites over the last 4 years, but the Craddock Bone Bed is our primary location. Our first field trips began in 2007, and we quickly met with success. What we have here on the left, this is Amy Taylor. She's the daughter of ranch owner Bill Whitley. She came out and joined us for some of our first sites, some of our first excavations, and she found one of the first Dimetrodon spines ever by the team. We were so excited, we named that part of the bone bed the Amy site. We had many other successes. We found other Dimetrodon parts. We found pieces of many other animals, but nothing said star attraction. Nothing, that is, until June of 2010. The team had returned to Seymour to close down the site for the summer. June temperatures were pushing into the hundreds, and that is no weather for field work. The plan was to finish up a little digging, tidy up the site, and then cover it with a very large tarp until fall. Now, when the team arrived at the site, they could see puddles from a previous day's rain, and there were more thunderstorms in the forecast. So David Temple, our curator, decided the best thing for him to do would be to dig some drainage trenches. These little ditches then could siphon away water so that any exposed bone would be protected. He grabbed his trenching shovel, about the size of your garden trowel, and he started at the bottom of the hill, working slowly up the grade, but steadily. Suddenly, he felt a familiar hardness. He stopped, put down his shovel, picked up his smaller tools, and gently began removing the matrix from the site. He had found bone. Over the next 2 days, and you can see this is the jaw right there, you can see the teeth. Over the next 2 days, Dr. Bacher determined that David had found the skull bones and jaw of a large Dimetrodon. Racing the coming rains, the team covered the exposed bone and closed the site for the season. They had a new skull, which they named Willi, after paleontologist Samuel Williston. Would they have more? The team returned in November to Seymour and quickly returned to their skull. They expanded their search site, and they found nothing. Then volunteer Kathy Zollfelt started removing a small ledge that was on Willie's east side. Suddenly she found shoulder, ribs, vertebra, and spine. More bones. What had once been the pathway into the quarry was quickly removed, exposing all of these bones, a complete torso. Willi would be our star. So I'll stop and point out what we've got here. So this is the vertebral column. These are the neural spines, the fin that you see, and these are his ribs, all there, every one of them. Kind of cool. And then once we got on the other side, the bottom layer of ribs too, so you have the entire rib cage, just kind of squished. So now in paleontology, there's a Murphy's Law with two parts. The first part is major discoveries always happen at the end of a season. And part two is when you're heavily involved in a particular project, another one will present itself. We had seen part one with our discovery of Willi. Now we would get part two. The Colthorpe brothers, Gary Max and Donald Gale, have run cattle on the ranch at the Craddock Ranch for many years, and they've seen many geologists and paleontologists exploring the ranch. Because of this, they've told their ranch hands to keep a sharp eye out for any unusual sights they might see in the rocks. Well, while our HMNS team was busy with Willi, the Colthorpe's crew was digging a new stock pond. When the bulldozer operator saw something unusual, he knew what to do. He went on over to the Craddock Bone Bed and asked our team members if they would come over and have a look. At first glance, they were really excited. They saw some wonderful botanical fossils, but then they looked at an area where they could see a little bit lower down, and they were amazed. It was full of amphibian skulls and jaws. Working with the ranch crew, our paleo team was able to extract a large block, 4 foot by 8, hence the name Big Block, the largest single block of rock ever removed from the Texas Permian. So now instead of 1 star attraction, we've got 2. But let's stop a minute and talk about what actually is a Dimetrodon. I've been throwing that word around. Let's define him now. So maybe you've seen toys of a Dimetrodon. You may recognize the shape, that fin. You're like, oh yeah, I've seen that guy before. Maybe you've been to our museum and you've seen the beautiful mural of the Dimetrodon surveying his domain. But what actually is he? Well, he's a vertebrate. And if you need to remember what that is, just reach back and feel your backbone there. He's a terrestrial vertebrate. He lived on land, not on the water. He was a pelycosaur. Okay, we're getting a little tricky here. Pelycosaur. Traditional classifications would call that a mammal-like reptile. But there's a modern cladistical classification that groups things differently by characteristics. And they would say he's a mammal ancestor with reptile characteristics. He's an amniote. That means that he has an egg that is adapted to be laid on land. And he's a synapsid. Now, synapsid refers to his skull shape. This is his skull. And we're going to be talking about this area right here. But I've got a map, so don't worry. There we go. So in amniotes, there are 4 basic skull shapes: anapsid, synapsid, diapsid, and eurypsid. Anapsids, you can see there's no extra hole back here behind the eye socket. And whether you're talking prehistorically or in modern times, if you're an anapsid, you're a turtle. Yeah, so hopefully that's what you guys are. So eurypsid have a small hole up here, high up behind the eye socket. That's represented by ichthyosaurs and sauropterygians. These are 2 marine mammals that lived during the time of dinosaurs. These guys are extinct, so we're not going to talk about them. But synapsids, here, with the single socket, the single hole behind the eye, these guys are represented by pelycosaurs, which Willi, Dimetrodons were one, and also then by therapsids. These guys evolved into these guys. These guys evolved into mammals. So we are synapsids. If you've ever chew, you can feel that right here. This is where your jawbone muscles go in. They connect. So everybody's a synapsid. Now diapsids, here with the 2 holes back here, are thecodonts. These are the guys that evolved into dinosaurs. And then modern times, the dinosaurs went on to evolve into birds and crocodiles, and also lizards and snakes. So to reiterate, we had an amniotic ancestor, a reptile, that just sort of branched out into all these different skull types. And you can see the synapsids. We have a pelycosaur. Dimetrodon were really kind of a dead-end branch on our tree, coming up to mammals. But dinosaurs, diapsids, are way over here. So what I really want you guys to come away with today, Dimetrodon is not a dinosaur, okay? If you remember nothing else, that's what we need to remember. So let's talk a little bit about, now that we know a little bit about who Willi was, let's talk a little bit about where he lived and what it was like. This is a geologic timescale. You all should have one on your desk. If not, I have more. This is the Permian period. It's the end of the Paleozoic. This purple part here is the age of dinosaurs. So he's just before the age of dinosaurs. Permian geography. The world was a different place 287 million years ago. All the continents had combined to form one large supercontinent called Pangaea. If you remember, the Earth's crust, the lithosphere, is made up of about 10 major plates that move through a process called plate tectonics. The movement is only about 3 to 4 centimeters a year, about the speed that your fingernails grow. Movements. But over a million years, the continents can align in many different configurations. Now, Pangaea ran from pole to pole, and because of that, oh, and by the way, Texas is here at the equator. And this little strip right here is where the red beds were. So we're right there on the equator. Because of this configuration, there's a major change in the paths of ocean currents. Ocean currents are the major drivers of climate and climate patterns, especially rain and land temperatures. This new supercontinent caused a major change in climate. How do we know that? Well, there are 2 ways. We do lithographic studies and paleobotanical studies. Lithographic studies basically means looking at the rock. And what we do here, we look for evaporites. Now, evaporites are simply minerals such as gypsum and salt that are left in the soil when the water evaporates, hence the name evaporite. So we have a strong presence of evaporites in the Permian, so that indicates there was a drying climate there. And a second way we study is we looking at the paleobotanical studies, the change in botanical fossils. Now these two maps show the growth zones, climate growth zones. This is in the end of the Carboniferous, just before the Permian, and this one is in the middle of the Permian. And what you're going to notice is down here in the southern continents, we still have glaciers and ice caps. If you look along the equator, you can see where Texas is, we're a rainforest. And we know that by looking at the fossil record in Texas, we see things called lycopods, which are the scale trees. They're still kind of ferns, but they're really tall, 100 feet long, scaly trunk. And we also have seed ferns. We have a lot of ferns during this time period. But if you look to the middle Permian, you see we've lost the dark green. We've lost the rainforest. Now we have what's called a tropical summer wet climate, which means it's going to be dry the rest of the time. And we see that represented by a change in the plant life. We have plants now that can handle a tougher soil condition, a drier climate. We see gymnosperms. So that change in botanical fossil record shows us that there was a climate change as well. Now, we've got studies that are done specifically local to Texas and studies that are done on a worldwide scale, and the data corroborates both ways. So we're pretty sure that that's a pretty good indication of a temperature change that way. Now let's talk a little bit about the animals that lived here. This is Willi's neighborhood. We have Willi here, we have Xenacanth, Diplocaulus, Trimerachus, Whitley raptor, Cecodont. We have all these guys there. The animals in this mural, this is sort of a mock-up, a pre-worked version of a mural that's probably going to be in the hall. And what it represents are animals that were found on the Craddock Ranch by the members of the Houston team. But we're going to break it down into subsections. No, it's not as good. All right. We have Dimetrodon. This is Willi, and we can tell because he's got that funky break in his fin. And Willi is fighting a Xenacanthus. So look at Willi a little bit. We see that he is a carnivore. The sharp teeth are the giveaway there. And not only that, but he's the first carnivore that was built to fight an animal his own size. Previously, carnivores were going after guys that were smaller than him. He's the first guy that could fight, well, other Dimetrodon. We found evidence for that. But also stuff like the Xenacanths and the other animals as well. Xenacanthus is a lobe-finned shark. These guys lived in shallow ponds, swampy areas, and it's thought that they could actually walk from pond to pond. If one was drying out, they could move. So the land shark jokes actually go pretty good right here. He's got this spine on his forehead that was poisonous, thought to be poisonous. Usually a spine like that is. And they're thought that it could probably move as well. So that's a protective mechanism for him as well. Other animals that we see some other pelycosaurs. We've got Whitley raptor here, which Whitley named after the family that owns the ranch. We're pretty sure this is a new species. He doesn't match completely with Dimetrodon. He doesn't match completely with Cecodontosaurus. Kind of a new guy. We have to find some more pieces, but so far evidence is that he's going to be a new species, and that's kind of cool to think that you've discovered something like that. Cecodontosaurus is another pelycosaur. You can see he's got a longer snout, so he can go into little burrowing things. He's a little smaller. He could get into where animals are burrowing, so he's got his own little niche. And then we have a guy back here, a Daphosaurus, who's a finback herbivore. We're filling all the niches now. We're starting to see that happen. Then we also have to talk about this little guy in the front, Uriops. Serious carnivore, about 6 feet long, 250, 300 pounds, amphibian, not your grandmother's frog. So this guy with the sharp teeth, he would have hunted. He had squatty legs. He wouldn't have gone very well on the ground, but he would have been like a crocodile in the water. So he would have been able to hunt that way and was very dangerous. And then the last two guys that we want to talk about are our Diplocaulus and our Trimerachus. Now these guys are small aquatic amphibians. Diplocaulus is nicknamed the boomer head. You can probably guess because of the boomerang-shaped head. People speculate why the boomerang-shaped head. You know, what could it possibly be good for? Some people have said as a foil as he moved through the water, maybe it was, you know, good that way. Most people think, though, because this is a really hard bone, and when you see animals today, like you think of deer, moose, you know, a lot of those animals, sheep, mating season, they do the headbutt thing. You see it in dinosaurs, too. You've got the little butt head guys. That he was one of those. And then Trimeranchus, this was the guy that was in our big block. So the amphibian skulls that we've had, this is the Trimeranchus. His name, Trimeranchus, means three-part spine, but his normal nickname, everybody calls him the Panzer Mud Puppy. Panzer because he had armored skin, bony plates, and then Mud Puppy because he was a bottom dweller. Both of these guys had short, squatty legs and would have moved poorly on land, but were great for being aquatics in the water. All right, so we found these things. Now let's talk about how a fossil forms and how we date them. Simply 4 steps on finding a fossil. An animal has to die and get buried. The soft tissues rot away and layers of sediment cover him up. Eventually those rock layers have to be exposed by erosion or tectonic activity so we can find them. And then a paleontologist has to look in the right type and right age of rock for his fossil. Well, gee, that's really quick. Why don't we just find these all the time? Well, it's harder than that. An animal has to die and be quickly buried. Terrestrial animals we hardly ever find as fossils because once they die and they lay out, they become the buffet table for everybody else. Scavenging is really, really bad, and the fact that, you know, I mean, everybody's seen, you know, their dog, you grab a bone and then go somewhere else to eat it. That's what usually happens here. Appears like it didn't happen with Willi, so the speculation is that he may have died around us where sandbar was forming. Sandbars tend to form pretty quickly, so he was at least partially buried fairly quickly. We see a couple of places where some of his ribs may have been gnawed and pulled a little bit, but not so bad that they were pulled and carried off because we still have them there in his body. So we're not real sure, but we're thinking he must have been buried somewhere near a little sandbar formation. The soft tissues rot away. Well, what happens there? You can imagine little bugs and insects and worms, and if he's near the water, little crustaceans, little crawfish are going to nibble away and eat all the soft parts that way. But you do have to have that sediment accumulation. He's got to eventually be buried to become a fossil. And then the rock layers, and here you can see the sediment forming. You can see the nice layers here in the rock, but you can also see the erosion that's occurred here, and that's one of the reasons that the Permian, that North Texas area, is such a great area because there's been such erosion. You can really find a lot of things. Everything's becoming exposed that way. And then the right paleontologist has to know what he's looking for. He has to know that he's looking in Permian rock that was terrestrial rock if he wants to find a Dimetrodon. Dating Willi. There's actually 3 ways that you can date a fossil. Biostratigraphy and biochronology are 2 of them. And basically, biostratigraphy refers to finding different fossils at different layers. You're going to think horizontally here. I found a particular type of fossil at this layer of rock, and at this higher layer of rock, I'm finding a different type of fossil. It lets you know which came first. So you're seeing a relative chronology of time that way. This has been around since really basically the beginnings of geology and the beginnings of paleontology, and was a tool that was used by geologists in forming that geologic time scale. And another thing that they noted too, that you can tell the deeper things are, the earlier fossils look less like modern animals today than the fossils that you find closer to us. So as we move through the fossil record, you can see a change in body type and shape as well. Now, one of the things with biostratigraphy is we have index fossils that help define the layers. There are certain fossils, especially marine fossils, for example, trilobites and ammonites, some of our marine-shaped fossils, that you find in the oceans all over the ocean. And if we find them all around the world, but each particular one in only a small layer, then those guys can really be used quickly to date a specific layer of rock, and we call those index fossils. Biochronology, though, rather than a horizontal thing, is a vertical thing. You're going to look at the length of time that one species is located in the fossil record. For example, the first time you see Dimetrodon is at the very beginnings of the Permian, and by the time you're midway through the late Permian, there are no more Dimetrodon. So there's a specific time frame where he's in the record. We use biochronology to note extinction events. But these are relative dating techniques. They give us an order, they give us a picture, but they don't give us an exact time. To do that, we use radiometric dating. Now, radiometric dating uses isotopes of certain elements that are radioactive. The isotopes decay at a constant rate that can be used to measure the rocks that they are in. And this unit of measure is called a half-life. The most well-known dating isotope is carbon-14. Its half-life is 5,730 years. It's great for archaeology and anthropology, but it's too short a time frame for older fossils, dinosaurs, things like that. What we use is potassium-40 and uranium-235. These guys have half-lives in the millions of years. And that means there's going to be enough isotope left to measure, even though all this time has passed. Now, these isotopes are found in crystals, in volcanic rock, and layers of volcanic ash. We heat the crystal, release the gas of the radioactive isotope, collect and measure the percent of normal element versus radioactive one. And that's all I'm going to say about that. Fossils aren't found in volcanic rock, though. They're found, remember we did the layering, you had to have the sediments. It's sedimentary rocks where you find the fossils. So to date something like that, what we have to do is hope that we have a layer of volcanic ash within our sedimentary rock. Now, has there any been found in Texas? No. However, just north of us in Oklahoma, in Fort Sill, we do have an ash layer. And then if you look at the biostratigraphy, you see that the fossil record is exactly the same in the same layers of rock. And so using the two techniques, the ash sample from Fort Sill and matching the species of fossils found, we date Willi for 287 to 285 million years old. So why? Why do we care? Why do we study these guys? Well, as Allison alluded to, we're curious about the extinction. Now, and she also alluded to the fact that the most famous extinction event is the dinosaurs. Everybody knows the dinosaurs aren't around anymore. But really, you only lose 11% of your families by just losing all the dinosaurs. If you look at the Permian, though, we lost 52% of all animal families at one time. Now, the majority of that was marine. We lost 90 to 95% marine fossils. And we see it starting really at the end of the early Permian, between our arroyo layer, where the Craddock Ranch is located, and that next layer up, the Vale. We lose 3 Dimetrodon species, the Adaphosaurus and the Cicadontosaurus, gone out of the record that early. And that just really started a slippery slope that culminated in all of this. 88% of the vertebrate genera are gone, 70% of all terrestrial vertebrates gone, 2/3 large animal species wiped out. Plants were okay. Who knows why? So why do we think this extinction had happened? We have no clue. You can tell by the number of theories that have happened. A great increase in temperature, a great decrease in temperature, change in atmospheric gases, drainage of shallow seas, increase in volcanic activity. There is a large volcanic activity going on in Siberia at this time, so maybe there's some truth in there. Meteorite impact. In the last, 6 or 7 years, since I've been at the museum, they've discovered a large crater, Permian time period, down in Antarctica. Maybe there's some truth in that. Probably it's a little bit of everything, but we'll just have to keep studying to find out more. But another reason for me to study the Permian is that there's major anatomical changes going on at this time. You realize we're moving from an aquatic environment to a terrestrial environment. And that means a lot of changes in our bodies. Now, we see those changes in our limbs, whether you're going from a fin to a flipper to a squatty little splayed leg to modern animals. And one thing that you have to realize is no matter what you've got, the blueprint for our limbs are the same. We've got 1 bone here, 2 bones here, a lot of bones in our wrist, and then fingers. That's if you're a fish, it's if you're an amphibian, if you're a frog, anybody. Everybody has that bone structure, but you can see a change in the shape of the bones as the structure, as the reasoning changed. We've gone from swimming, we've gone from crawling, now to running. Dimetrodon's the first guy that can sort of run slowly, clumsily, but it's a start, and that's the first time that you see that pattern and that ability on land. Ear changes. Our ear bones, if you really take the history back, started as gill arches in fish. Goes on to lower jaw bones, no problem. Goes on to lower jaw bones in reptiles, and then to our middle ear bones today. So all of this change goes on at the same time. Dentition, our teeth, guts, all of that changed. Now we have herbivores for really the first time. We have these guys that are eating all these plants. To do that, you have to change your teeth. Sharp pointy teeth aren't good for chewing and masticating plant material, those leaves and stuff. Our guts have to elongate. Anybody that's an herbivore has a lot longer gut than guys that are carnivores. And to digest really plant material, you've got to have microbes in your gut. Well, when did that get introduced? During the Permian. We start seeing all of these changes in body formation. And the pelycosaurs are, Willi being, the synapsid like that, he's the one that we see this starting in. So we study these guys because these early synapsids are us, 1.0. So let's get back to Willi's story, because this is the fun part. So we discovered Willi, we got all the ground off of him, and the first thing we did was cover him back up, but with a plaster jacket. You can see by looking at the countryside here, we do not have outdoor plumbing, so everything has to be brought in. We bring in the water, we bring in the plaster. You mix the plaster and water together. We use burlap strips, about an arm length of strip, 4 inches wide for each one. And the first thing we do is we cover the specimen with either foil or newsprint, and then we start layering plaster over the top. Once that happens, the next step is to start digging a trench around that outside frame of the specimen. You don't just dig and throw, though. You have to collect all the rock that goes around, looking to make sure there's no little small bones. Guys about like this size that you're going to find in your matrix. And everything that even if you don't find bones, you collect that matrix, you put it in a Ziploc baggie, you label it, and it goes back to the museum to be washed and screened. So you get all the way down, and as you're digging down, you're adding more plaster to the sides, to the sides, to the sides, and finally you get down far enough to where you realize that you can start undercutting and you're not going to run into your guy anymore. So, and as you do it, you keep adding and adding and adding. The next step then, once we've got him ready to go, we had reinforced his jacket with 2x4s. Now you start undercutting, getting that underburden out from under him, and you just leave little pillars there. We decided that because of his size, he was about 5 foot by 5 foot, we were afraid as we flipped him it might torque a little bit, and we were afraid we would break some of those thin bones, so we decided to screw a pallet onto the top of the jacket. So we've got it all ready. We've got the pallet on, we've got extra packing straps all around it. We've walked around it as many times as we can. We've looked under it as many times as we can. It's time to call the Colthorpe brothers to bring their front-end loader. The tension was high. Anxiety, you could cut it with a knife. It was just really tense. Everybody was just, should we do it? Should we wait? I don't know, maybe we should try tomorrow. No, we really need to do this. Yeah, we really need to do this. It's got to. Okay, so we started the flip. So far, so good. We get the prongs of the front end loader underneath the pallet, get him loaded onto the pallet. We're feeling a little bit better. And get him out of the quarry. Willi is free at last. It was a parade-like atmosphere from then on. Excitement, cameras pulled out of every backpack, out of every car. You would think a celebrity had come to Seymour. Loaded him into the trailer, and for the first time in his life, Willi was leaving Seymour. We took Willi to the Black Hills Institute in Hill City, South Dakota. The Black Hills Institute is run by Pete and Neil Larson. They hunt fossils, collect fossils for themselves, but they also clean fossils for other museums, and they mount them. And then they also they build casts. They make casts for everybody else. But what's really nice is they do all of this, and they are working for our museum to build some things, but they allow our volunteers to come up and use their facility for free. So we get to use all their equipment, and we get to use their stuff, so it's really amazing. So step one of cleaning Willi was to take all of that matrix, all of that rock that was in the jacket still, and clear it away. And this is what he looked like once we'd gotten the matrix off the top of the jacket. You can see his shoulder, you can see all the spine, and you can see his neural spines, the fin, and then you can see his ribs. You can see a couple have been pulled, but they're still with the body there. The second step then was to actually label every bone and then start pulling them out so that they could be cleaned under a microscope. Every bone gets put into a little foil packet, like you'll get to see up here, and it is then stuck in a Tupperware for protection, and then everything's taken out one at a time and cleaned. We use a little bit of acetic acid, a little vinegar and water solution to try to get that last little bit of clay that's kind of glued onto the bone. If we can't get it off, then the Black Hills people have an air abrader. They have a little air gun that they can use professionally to do that. The next thing that they will do then is they will weld together a mount out of steel to mount those real bones onto a frame so that we can then show him at the museum. Other projects that the Black Hills Institute are doing is that they're making the molds, then building the casts for us, and then they are going to be cleaning the big block, the Trimeranchus skulls. You can get a good view. You can see these little skull guys, and doing that. So that's sort of what they do. But we need to stop and talk about something. Building a cast, I mentioned that. When I take people through the Paleo Hall, it doesn't matter if they're 5, 50, or 500. The first thing out of their mouth is the same question. Are the bones real? Everybody wants to know. And the answer is some of them are and some of them aren't. Well, why is it important to make a cast? Well, I can think of 3 reasons right off the top of my head. If you have a mostly complete skeleton, do you just put him up there and leave a part of his head missing or have him missing a leg? It isn't aesthetically pleasing to have an incomplete skeleton when you have a part that you can build to make it complete so then you can show the public really what he looked like. But mainly, if you think about it, there aren't very many T-Rex skeletons in the world. Certainly not enough to go into every science museum worldwide. And if you're a science museum, you can't not have a T-Rex. I mean, that's what everybody wants to see. You can't talk about the Cretaceous period and leave out the apex predator, the top guy that's eating everybody else. You can't just not have that. You need to have the visual there for the public so you can finish telling the story. And then another reason is that it allows us to do some really dynamic posing. When we use a real bone skeleton, yeah, the awe factor is huge. Oh my gosh, look, those are real bones, wow. But we have to be so careful. Besides being anatomically correct, the next most important thing is making sure you're not damaging the bone. So you are only posing something in the most static, most ergonomically correct way, just the way that nothing is going to wiggle. If he's on 4 legs, you're not even going to lift up one paw. He's just going to be static. Whereas if you have a cast, you can have him running. You can have 2 animals fighting, and you can expand your story, and the public can see the visual that way. So that's the reason why museums use both casts and real bones. Yeah, the awe factor is good, and you need some of that, but you also need to be able to show these guys in an interactive pose, and that's why we use casts. But while all of this is going on with Willi, while he's getting his final tune-ups and cleaning, we've been busy beavers down at the museum as well, trying to get the new exhibit hall built out for you guys to come. The hall's expanding to the size of a football field, 2 stories tall. It's big. And a lot of things are going on. Murals are being designed, maps are being highlighted, text panels are being written. Style of text panel is being argued about. Cases are being built for smaller specimens, lighting issues. There's some new lighting style to better highlight that. Platforms are being built for larger ones. There's a balance between the optimal layout to present to these guys and an optimum flow pattern for visitors. And you've got to really mesh these 2 things together. But it's all geared for one objective, and that's getting the public, you guys, to stop, to look, and to learn. That's why we've been finding Willi, and I think it's a role that he was born to play. And I'm done. Questions? Got it.